All right, on this video, we're going to work out finding the solution for a linear system of differential equations with complex eigenvalues. Before you try this, you should definitely have worked out several writing solutions for linear systems with real eigenvalues. Previous videos, I've done some examples of that. So you definitely want to know how to do those first. This is kind of a worst case scenario. Most of the time, you're really only responsible to determine the stability. If you end up with complex eigenvalues, being able to decide whether it's a stable spiral, a neutral spiral, or an unstable spiral, and that's it. Sometimes, though, you will get asked, not always, to write the solution. And it's, as you might expect for complex eigenvalues, writing the solution is a little complex as well. So let's do one example here. So here's the matrix associated with my linear system, and this is my initial condition. So first step is we still do need to find the eigenvalues. In the normal way, the determinant of A minus lambda I, which as you should know is the determinant, what's going to happen is the main diagonals are going to get that lambda minus lambda. And we set that equal to 0. My determinant is the product of the main diagonals, which are identical in this case. So I have -1 minus lambda times -1 minus lambda minus the product of the off diagonal, which is -6. Set that equal to 0. Because these are identical, rather than foiling it out, I think I'm going to write this as -1 minus lambda squared. This is really +6, but I'm going to move that over to the other side of the equation, because then I could do the square root method where I solve this by taking plus or minus the square root of both sides of the equation. So I have -1 minus lambda plus or minus the square root of -6, which is plus or minus the square root of -1 times the square root of 6. And of course, the square root of -1 is I. So I could write this as plus or minus I root 6. If I add the 1 over, 1 plus or minus I root 6, and then multiply both sides by -1, this will become negative, but of course, plus or minus, if I multiply it by -1, will be negative plus. So it's basically the same thing. So I end up with -1 plus or minus I root 6. One nice thing about working with complex eigenvalues, normally you get two different eigenvalues and you have to find eigenvectors that go along with each eigenvalue. It turns out with complex eigenvalues, they're always going to be what we call complex conjugates. One of my eigenvalues is -1 plus I root 6. The other one's -1 minus I root 6. That's what we mean by a complex conjugate. And it turns out that you don't need to work with both eigenvalues and eigenvectors, because what happens if you do that, you could end up combining your solution into a shorter solution. I don't know if that makes any sense, but it turns out you just need to work with one of your eigenvalues and its corresponding eigenvector. So we're just going to use the positive one. We'll use -1 plus I root 6. So we need to find the eigenvector that goes along with this. We'll do it the same way, where we take our matrix times the eigenvector is equal to lambda times our eigenvector. So we're going to have -1, 2, -3, -1 times my vector, I don't know yet, equals my eigenvalue, -1 plus I root 6 times my vector, my eigenvector. If I multiply out the first row times the column, I end up with -x1 plus 2x2 equals this times x1. So what I'm going to actually do is just kind of distribute this. So I'll end up with -x1 plus I root 6 times x1. And as always, if I can get a relationship between x1 and x2 from just this equation, I don't need to worry about the bottom multiplication. It's going to give me the same relationship. Sure enough, in this case, x1s cancel. I can solve for either one. Maybe I'll solve for x2. X2 would be I root 6 x1 divided by 2. And so the easiest way to find an eigenvector without having fractions, what I'm going to do is choose x1 to be equal to 2. Choose x1 equal to 2. You see why? Because if x1 is 2, then x2 is going to be 2 over 2, which is going to cancel. x2 is going to be I root 6. So my eigenvector is x1 is 2, x2 is I root 6. Okay. Now we're going to use a shortened version because we're only working with one of our eigenvalues and eigenvectors. The normal solution we're used to is C1 e to the lambda 1t times V1 plus C2 e to the lambda 2t times its eigenvector. But since we're only working with one eigenvalue and one eigenvector, it's just going to be this, but you're going to see it's still going to get kind of ugly. So we're going to have some constant e to the negative 1 plus I root 6 t times our vector, 2 I root 6. And then at this point, well, actually, hang on. Let's distribute the t. So this becomes c e to the negative t plus I root 6 t times my vector. We're going to split this up into multiplication. So we can think of this as c e to the negative t times e to the I root 6 t. Times my eigenvector. And this is where we're going to use, we've discussed this before. If not, go back and watch an earlier video. Euler's formula. Euler's formula says e to the I theta is equal to cosine theta plus I times the sine of theta. So if we kind of match this up, I have e to the I root 6t. So this is going to be like my theta. And I'm going to plug, that means I can replace e to the I times root 6t with this, with theta being root 6t. So it's going to look like this. C e to the negative t times cosine of root 6t plus I sine of root 6t times my eigenvector. I got to ask this, and I should have, but I'll go ahead and do it right now. When we had our eigen value of -1, go back page, -1 plus I root 6 was our eigenvalue. Remember, from there, you can determine the stability. Because it's complex, we know it's going to be a spiral, and because the real part of our eigenvalue is negative, the stability is going to be a stable spiral. We already should know that the minute we knew our eigenvalue. Okay. Anyhow, that's sort of backtracking a little bit. We're working on writing the solution now, so we're getting there. But I guess what it made me think of that is we can now see why this would be a stable spiral. This is going to get smaller as t gets bigger. And now that we've introduced sine and cosine, that's going to cause spiraling action, right? Because sine and cosine create like waves. Anyhow, keep going here. So now what we're going to do is take this and multiply it into my vector. So I'm going to make this one big vector, and I'm going to have 2 cosine root 6t plus 2I sine of root 6t. And then this is going to get multiplied. So I have I cosine root 6t plus, okay, ready? I root 6 times I is going to be I squared root 6 times sine of root 6 t. And of course, we know that I squared is just the same as -1. So I could write this as CE to the negative t. Well, here's what we're going to do next. Okay, that's -1. So this is just -1. What we're going to do now is separate this out into two separate vectors where we have the real parts of each one. So notice like this is the real part of this first line, and the real part on the bottom line is now this, because this is now negative root 6 sine of root 6t. So I'm going to put the real part here, 2 cosine root 6t. This is negative root 6 sine of root 6t. The other two terms are both imaginary. And so what I'm going to do is factor out the I from both of those. I times, for the top one, I have 2 sine of root 6t. For the bottom one, I'm just going to have cosine of root 6t. So these were the real parts, and these were the imaginary. Okay, next step. I'm going to distribute this constant c in here. And this is where it's a little bit kind of weird here. But if I distribute this constant here, I'm going to have e to the negative t times some constant. I'm going to call that c1. 2 cosine root 6t negative root 6 sine root 6t. Now here's the thing. This is a little strange, I know. If I take a constant times I, I'm just going to call that another constant times this vector. That seems a little weird, but I'm not claiming that constant has to be real, right? A constant times I, this could be imaginary too, right? I'm just going to call it C2 though. So C2 is C times I. Cosine root 6t. And this is, right now, this is our general solution. Remember, our general solution we can write as x bar of t. So this is our general solution. If you have initial conditions, which we did, we can now plug them in to solve for our constants. Now plug in initial conditions. We were told that x of 0 was equal to the vector 2, 0. So what that means is 2, 0 is going to be what I get if I plug in 0 for t to all of this mess. E to the 0, c, oops, let's make that parentheses, c1, 2 times the cosine. If I plug in 0 here, I know it's root 6, but it's root 6 times 0. So this is just going to be the cosine of 0. This is going to be negative root 6 times the sine of 0 plus c2. If I plug in 0, that's going to be 2 times the sine of 0, and this is going to be the cosine of 0. Now, of course, the sine of 0 is 0, so this term is 0, this term is 0. The cosine of 0 is equal to 1. This equals 1, and this equals 1. So what that means then is 2, 0, e to the 0 is 1, so I'm just going to get c1 times 2 times 1 is 2, so that's 2c1 plus c2 times 0. That gets wiped out, c2 times 0. And for the bottom one, I get c1 times 0, which gets wiped out, plus c2 times 1. So if I just look at the top numbers, I have 2 equals 2C1, which means C1 is equal to 1, and 0 equals C2. Okay, so if C2 is 0, let's go back to our general solution. In this particular case, because C2 is 0, that's going to, if this is 0, it's going to wipe out this part of my solution. And to get my final solution, all I have to do is take this C1 is equal to 1, put that in here. Of course, C1 being 1, you're not going to notice it. So my final solution is going to be x of t is equal to e to the negative t times C1, but that's just 1, times 2 cosine of root 6t negative root 6 sine of root 6t. Told you it was not going to be easy, but it's definitely doable. If you go through that a few times, you might want to try it over again and refer back to the video if you get stuck. All right, there you go.